Hello, boss. Morning, sir. Happy weekend. So, uh, fún fídíò RBCL tẹ́ send yìí. So this is just the illustration of how I went about it using Unipro UGENE software. So this is the software UGENE. So I had to download the bin file you sent to me to the file a document file. So I think this is bin. Yes, this is the file you sent the other day. So I'm going to extract the sequence. So this is the chromatogram and the open reading frame. It is having two open reading frame that is coding for an expressive protein that can be expressed. But that is not where we are actually going. Where we are actually going is to see the uh, to get the sequence. And in getting the sequence, we need to uh, open it up. Okay. All right. So I have to get it this way. So this is the sequence now. We can check some other things about the sequence if we want to check the complementary. If we want to, this is the complementary. This is the wrap sequence. This is to show the translation and to show the open reading frame. So, but what I need is to get out this sequence, which is for me to left click and select sequence region. So the sequence is 572 in number. So what I'll just do is just to select everything. I selected everything, but if it is a particular region I need, I'm just going to use the open reading frame information to get that. So for the open reading frame, it's starting from nucleotide 336 to 4452, which is 117 length for this first one. Then the second one is having 462 to 572, which is 111 length. Then the third one, which is this last one, is 314 to 571, which is the longest open reading frame. And it is 258. What are they calling it? 258 DNA nucleotide long. So that, but that is not where I'm going. So this sequence, which is 1 to 572, have three open reading frame. And based on what you said the other day, it's this open reading frame that I used to design the primer. So I was able to use NCBI to pick out region between from 314 to 571 of this sequence. So I had to pick out this sequence, save it. What I did was copy selected sequence. Then I had to open up a notepad in the file folder. So I open up a text document. Okay. Let me say this is the text document. This is the sequence. So I want to make it a faster format, normal now. Put my greater than sign and I have to put RBCL chain. So this is the subject. This is the subject gene. So what I did was I saved this up. When I save this, and it is this sequence I now use to run the blasts for primer blasts. I now pick primer based on the region which this what are they calling this longest open reading frame is telling me. So whichever primer I'm going to design will be a primer that sits within this region. Yes, this is the region. This is the sequence. So we can easily just look at how the nucleotide is being arranged. Look at the GC contents where GC is much to pick region where we will just tell the NCBI algorithm to design primer for us. But that is not where we are going. So after I've been able to do this, what we are actually going to do is I have run the blast to get this similar. I have run the that's nucleotide blast, nucleotide to nucleotide blast to get the amino acid sequence that we are going to be using for the phylogenetic tree. So this is the one I just this is the one I just this is the one I just did now for the sequence you sent. So this is the previous one I did. The previous one I did. Oh, this is not. This is okay. This is it. Now this is the subject RBCL gene, which I copied. The way I did it, the initial time, that is the way I did it. I now pasted it here. Then when I run the blast, I was able to get all these similar protein nucleotide rather that are close to it, which is what I sent the image the other day. So I picked the first 50. So there are several sequence. So what I did was I downloaded the aligned sequence alone of the sequences of these plants, the aligned area alone rather. So they are complete genome. I downloaded the complete genome too. So this other one, this other video here, this other file here is the complete genome. Now this is Bauerinia racemosa. This is the complete genome. But on this file, this is Bao Baonia rhythmosa. This is just the sequence, the area of the sequence, nucleotide sequence that is complementary to this our test subject, RBCL. So this is having just the segment that we need, while this other one is having the complete genome of each of these nucleotide which we use to run the blast. So we can decide to want to use this later or we can decide not to. So this one is having much more numerous nucleotide sequence, unlike this one that is just having the region in that sequence that is complementary to our subject RBCA. So now that we have gotten the sequence, what we need to do now is to save it, which I've saved now. I've saved my subject sequence and I have the 50 other sequences that are complementary, that are close based on similarity, percentage similarity. So now I have blast sequence aligned RBCL gene. So I already saved this. So what I will now do now is I will close this. I don't need this sequence again, or I might leave it and start a new project. So I'll open this sequence, which is the uh, last blast sequence aligned RBCL gene. So it's going to tell me, do I want to open it as in a sequence file, or I want to merge it together, or I want to compile it in an alignment sequence, or I want to map it. But it is best that we open it as a separate sequence first to see the open reading frame of each of these sequences that we downloaded as similar to our subject RBCL. So I'll just okay it. So these are these are the sequences. These are the sequences. That is, there are 51 like that. So this is the reading frame area where we can see the open reading frame. If you notice, you are going to see that most of them are having their open reading frame at the end side of this. What are they calling it? This amino acid sequence, and information about the open reading frame is here. If you want to check it one by one, we can see information about the length here, but that is not where we are going. So where we are going is that we need to copy all these sequences that we have lifted. So I'm going to click on one and highlight it down to the last one. So this is our subject sequence. So I'm going to left click and export it. I'm going to be exporting it to an alignment file that is recognized by this software, which is the cluster alignment. So now I want to save it. It's already in cluster. I might decide to save it in faster and any other uh, format. But I'm going to be saving it in cluster because that's what we are going to be using to run our alignment. So the region or the place I want to save it, I'm going to name it, select it. So I still want to save it in the file loop. So I'm going to name this one aligned RBCL genes. So and it's going to be saving the cluster W format. So I'm saving it. So I will now click on export. Now this is my export. These are my export rather. So these are the sequences. I can see information about the sequences from up to toe, from down, top to bottom. But I want to make the subject one the reference chain. So what I will just do is I'm going to click on it and right click on it and set this as reference. So because I've set this as reference, I'm going to have to move it up so that others can be down. I want it to be up. So this is just an rearrange sequence now. It is not yet aligned. So for us to align this sequence, I'm just going to click on one of them and come to alignment. Now, I'm going to be aligning using muzzle because uh, that is one of the alignment tool that is being used in this software. Now there is align with cluster, there is align with maft, there is align with muzzle, align with tea coffee. So if we align with cluster, I've been able to try to align with cluster before, but there are errors or there is issue with the alignment algorithm. So we can see the percentage here. Let's look how it's going to turn out to be. So it's running the alignment. Okay. Thank God the alignment worked today because the last time I did it with cluster W did not go. So these are the sequences and it is being aligned. Now, if you notice, you are going to see that each of these are sequences at some point they are having similar nucleotide coming together. Like in this place where there is A, there is T down, there is T down, there is A down. But because we are having gaps in some of these sequences, we are having gaps in some of these sequences, and that gap is not going to be useful for us. We are going to need to clip and cut. Now, if you look at the other end, we are also having gaps, similar also in this place. So the best thing for us to do is we have to clip out those gaps, that part of this sequence that is not going to be useful for our tree. So for us to do that, I will have to cut out from this part and click A. I'm going to have to click out, cut out from this place, and let it get to this part where we are having a gap in our sequence. So I'm going to have to drag it down so we can see, okay, it has been able to copy all the region where there is a gap. So the reason why we are bringing it down to this A is because of this our sequence for this what are they calling it? JX856643.1.1 dash 542 is having a very long gap. So we have to delete those gap out. So it's going to eliminate this region, leaving this other part. So this our AATT is going to start as the number one. So delete. Now you can notice that it has deleted those gaps out. So we're having AATT as our first part. So the same way we are going to do for this other part too, we are going to need to uh, clip out this region and also delete it out so that we can have a more balanced sequence for our phyllo analysis. So this also I'm going to delete. So I'm left with a well arranged sequence. So we can see certain region of this sequence where there are polymorphism. Yes, let me put it that way. Variations as a result of polymorphism, change in their sequences. We can look at this place, we can see that from this C to this region, all the sequences are having the same amino acid arrangement. So that is to tell us that our sequence has been properly aligned. So this is what we are going to be using to build or develop our phylogeny tree. So depending on the kind of phylogeny we want to build, maybe we are going to be building a neighboring uh, neighborhood kind of like phylogenetic tree. So we can click on any one of these our sequence, this consensus parts. I've been able to make it uh, align, forming an appropriate or a fine consensus. So the next thing is I right click and we want to build tree. So the kind of tree we want to now build with is going to determine or depend on what we want to build our tree for. So the common type of tree we used to build or that they used to build in a phylogenetic analysis is a neighbor joining or maximum likelihood. So because of this analysis, I'm going to be using the neighbor joining tree, and the distant matrix is going to be we are going to leave it at default, but we are going to need to set the bootstrap so that it can have to like help us construct a tree in a 100 replica, which is the normal way if we want to use mega to develop or design our phylogenetic tree. So we have to design our tree in such a way that it's going to be designing the tree, each of these sequence as a replica in 100 places so that if there are errors, it is going to be minimal. So every other information in this place too is going to be left at default. So we are going to build. So when we click on build, we are going to see that the building is being carried out. It's conducted in this region. So this is almost 80%. So we are going to see how our tree will look like. I feel this one is much easier because it's all in one, it's all in one, what are they calling it? All in one software. We can see our sequence, we can see the, what are they calling it? We can see the, yes, this is now the phylogenetic tree. How do I make it? Okay. Okay. Trying to make this look bigger so that we can both see it properly.
ṣé kò sí nǹkan kan létí ìrìn lè tẹ̀sí kò sọ́gbìn.